Hey guys, welcome back to a new video. And this video in particular will be the first one in dark mode, meaning with a black background, because roughly 60% of you voted that you would prefer videos with a black background. And so here we are. Of course, it's just an experiment, so let me know in the comments what you think of it. And now for the topic at hand, slanted asymptotes. These are basically asymptotes that are not horizontal, not vertical, but any other straight line that you can imagine. And as we know, straight lines are described by a linear function, a times x plus b. And as always, to understand this concept, in this video we'll be doing several exercises where we need to find the slanted asymptote, so this a and b, for specific functions. And before we go into the exercises, I will briefly cover the method that we'll be using and specifically why it works, because this will give you a better understanding and therefore makes it much easier to remember how to solve these exercises when you actually need it. And of course, as in any of my videos, the timestamp for each exercise can be found in the comment section down below, where you can also ask any questions you might have. And with that said, let's get into it. Let's first briefly look at the general solution of finding a slanted asymptote and see why exactly it works. Let's say that you have a function f of x, which is a general function, of which you want to find whether it has a slanted asymptote, and if it does, to find its expression, meaning to find a linear function. And let's now assume that the function that we're looking at, f of x, can be written as the ratio of two other functions of x, h of x in the enumerator divided by g of x in the denominator. And this brings us to the first rule, which is that if the highest power of x in the enumerator, meaning the order of h of x, is equal to the highest power of x in the denominator plus 1, meaning the order of g of x plus 1, then and only then will we have a slanted asymptote. And this rule of course makes it very easy to rapidly spot whether a function f of x has a slanted asymptote or not. Just look at the highest power of x in the enumerator and compare it with the highest power of x in the denominator. If it is 1 larger than in the denominator, then indeed you have a slanted asymptote. Now this rule is all too easy to just learn by heart, but oftentimes at the situations where it really matters, your memory might fall short. That's why it's very important to understand why this is actually the rule, or why it actually works like this. And the first point is to realize that an asymptote is actually a limiting case. It's to look at the behavior of our function f of x when x goes to plus or minus infinity. Of course, not all functions have asymptotes, and not all asymptotes are slanted asymptotes. We could have vertical asymptotes or divergences, or we could have horizontal asymptotes as well. That's why we need to combine this with the second point, which says that a slanted asymptote is actually a linear curve. Taking these 2 points together, we find that if x becomes either very large or very negative, that our initial function f of x, which is equal to the ratio of h of x divided by g of x, will tend towards a linear function, ax plus b. And we know from our knowledge of limits that this will only be the case if the order of the function in the enumerator, h of x, will be 1 larger than the order of the function in the denominator. Only in that case is it possible that this function reduces to a linear function. And this is why our rule to determine whether a function has a slanted asymptote actually works. So once that you've determined that this function indeed has a slanted asymptote by using rule 1, we go to rule 2 to actually find this a and b of the slanted asymptote, which is long division, meaning that this function f of x that we had that could be written as the ratio of two functions, that we will perform a long division on this ratio. And then afterwards, we will perform a limit when x goes to plus or minus infinity on the result of this long division. So basically finding the slanted asymptote comes down to performing a long division. If you can do long division, then you can easily find slanted asymptotes. So let's now put these two rules to the test and go to the exercises. In the first exercise, we are looking at the function f of x, which is equal to x squared minus 9 divided by 2x minus 4. And the exercise here, obviously, is to find whether it has a slanted asymptote, and if it does, to find its equation. And the first rule says that we indeed have a slanted asymptote if the order of the enumerator is 1 larger than the order in the denominator. So let's see, we have in the enumerator the order of x squared minus 2, and in the denominator we have the order of 2x minus 4. Now the order of a polynomial is simply the highest power of x. So here we clearly see that we have x squared in the enumerator, so we have an order of 2, and in the denominator we have an order of 1. And we see indeed that the order of the enumerator is indeed 1 larger than the order in the denominator. So we indeed have a slanted asymptote. So now we need to find it by performing first a long division. And then afterwards, we will take the limit of x going to plus or minus infinity from our result. So let's perform a long division. We have x squared minus 9 here. Then we draw our long division lines, and we divide by 2x minus 4. The first step in long division is to divide this x squared by this 2x, and we write the result underneath it. So we get 1/2 times x. The second step is to now multiply this 1/2 times x with both of these terms right here. The first multiplication is this 1/2 x times 2x, and we again get x squared, which is how we got this 1/2 x in the first place. Then the second multiplication is this 1/2 x times minus 4. This will give us minus 2x. What we then do is we subtract these two polynomials from each other, the upper one and the lower one that we just got. So x squared minus x squared is of course 0. Then we have 0 times x in the upper polynomial minus negative 2x, which of course becomes plus 2x. And we're left with this minus 9, which we just subtract 0 from, so we are stuck with this minus 9. And at this point, all of these steps repeat. We take this 2x here, and we divide it by 2x over here, and this simply becomes plus 1. Then we multiply what we got here with both of the terms here and here. This gives us first plus 1 multiplied by 2x, which gives us 2x. Then we multiply plus 1 with minus 4, and this gives us, of course, minus 4. Then we subtract these two polynomials again, so we get 2x minus 2x, which is 0. Then we get minus 9 minus negative 4, which is, of course, minus 9 plus 4, and we get minus 5. And at this point, since the power of x in the thing that we are left with is larger than the power of x of the leftmost term right here, we come to a halt. And we conclude the following, that our original function, x squared minus 9 divided by 2x minus 4, can be written as follows. 1/2 times x plus 1, which is the result that we got right here, and of course our rest term, which is this minus 5 that we've gotten. So minus 5 divided by the original denominator, 2x minus 4. And now that we've rewritten our original fraction of two equations, we can perform our limit of x going to plus or minus infinity. And this will be the last step in order to find our slanted asymptote. So let's take this limit. We have the limit of x going to plus or minus infinity of the following function, namely the function that we found. 1/2 times x plus 1 minus 5 divided by 2x minus 4. And we're not exactly going to perform this limit, we're only going to notice that this term here drops out because this x in the denominator becomes very large or very large in the negative sense. Therefore, it can simply be dropped. And we see what remains is this linear function right here, 1/2 times x plus 1. And this function will be the function that describes our slanted asymptote. Because what we see here is that our original function, f of x, could be written through a long division as this green function right here. And we see that in the limit of a very large positive or negative x, this function in the limit reduces to a linear function. And then this linear function will approximate our original function when x becomes very large or very slow, the exact definition of an asymptote. And with this first example done, let's now go to the second exercise, where we have our function f of x, which is equal to 2x squared minus x minus 3 divided by x minus 2. And of course here the task is to find whether this function has a slanted asymptote, and if it does, to find its prescription. The first step to see whether this function indeed does have a slanted asymptote is to find the order of the enumerator, so the order of 2x squared minus x minus 3, divided by the order of the denominator, so the order of x minus 2. Remembering that the order of a polynomial is simply the highest degree of x, we find of course that we have 2 divided by 1. And again, the enumerator is simply the denominator plus 1. And therefore, we conclude that this function indeed does have a slanted asymptote. And in order to find the prescription for this slanted asymptote, we're again going to perform a long division on our original function. So we have 2x squared minus x minus 3 that we're going to long divide, if that's even a term, by x minus 2. And again, we take the leftmost term on this side and we divide it by the leftmost term on the other side. And this gives us, in this case, 2 times x. And then we multiply this 2 times x with each of the terms of the polynomial by which we are dividing. The first multiplication is 2x times x. This of course will be 2x squared. Then we have 2x multiplied with minus 2. This gives us minus 4x. And we can write a minus 0 here to make it more symmetrical. Then in the next step, we subtract both of these polynomials. The first term gives us 0. The second term gives us minus x minus negative minus 4x, which is minus x plus 4x, which is of course 3x. And for the last term, we simply have minus 3 minus 0, which is simply minus 3. Then all of the steps repeat. We divide this term by this term, which in this case simply gives us plus 3. And then we multiply this plus 3 with both of the terms in this polynomial. The first multiplication is plus 3 multiplied by x, which gives us, of course, 3x. Then we multiply this plus 3 with minus 2. This gives us minus 6. And again, we subtract these two polynomials. We get 0, minus 3, minus negative 6, which is, of course, minus 3 plus 6. And this gives us plus 3, which is our rest term. So what we found from this long division is that our function, f of x, can be written as follows. We have the result of our long division, 2x plus 3, so it will be 2x plus 3, plus our rest term, which is 3 divided by our original polynomial, x minus 2. And now as the last step, we can perform our limit of x going to plus or minus infinity of exactly this function, 2x plus 3 plus 3 divided by x minus 2. And this of course will give us our prescription for the slanted asymptote, because if x becomes very large, then this term right here cancels out because we have an x in the denominator. And we are left with this linear function right here. This means that the answer to this question is that the slanted asymptote has a function of 2x plus 3. And this linear function will be the slanted asymptote when x becomes very, very large of our original function. Let's now go to the third exercise. Here we're looking at a function, f of x, which is equal to 3x minus 5 divided by x plus 1. And again, we're asked to find the slanted asymptote. And the first step, of course, is to look whether this function indeed has a slanted asymptote. So we look at the order of the polynomial in the enumerator, so the order of 3x minus 5, and we divide this by the order of the polynomial in the denominator, so the polynomial of x plus 1. Now we see in the enumerator, the highest power of x is simply 1. So we have 1. And in the denominator, we also have the highest degree of x being 1. So we simply have 1 divided by 1. And we see clearly that in this case, the enumerator is not 1 more than the denominator. And therefore, we do not expect this function to have a slanted asymptote. And normally you would just leave it at this and go to the next exercise. However, for good measure, let's now consider the case where you indeed forgot this rule right here to determine whether this function actually has a slanted asymptote. And the only thing that you remembered of slanted asymptotes is that you had to do a long division. So let's now just proceed with our method as if we didn't know that this function didn't have a slanted asymptote, just to see what happens and to even get a better understanding. So we just perform the long division, dividing 3x minus 5 by x plus 1. And then again, we draw our long division lines and we can start. And again, we divide this 3x by this x right here, and we get, of course, simply 3. Then we multiply this 3 with each of these two terms in this polynomial, and we get for the first multiplication simply 3x, so 3x. And for the second one, we have simply 3 multiplied with 1, which is, of course, plus 3. If we subtract these two polynomials that we obtain, then we simply get 0 for the first term and minus 5 minus 3, which is of course minus 8. And since this minus 8 has a lower power of x than this x right here, this is the end of the long division. And what we conclude is that we can write f of x simply as 3 minus 8 divided by x plus 1. Simply our result of the long division minus our rest term. And the next step in our procedure is of course to take the limit of x going to plus or minus infinity. In this case, we take the limit of 3 minus 8 divided by x plus 1. And if we do this limit, then we see that indeed this x becomes very large, so this entire term here drops. And what remains in this case is simply 3, not a linear function. And this basically means that we indeed do not have a slanted asymptote, as we found by applying our first rule right here. But what we found is that our function, f of x, now reduces to simply a number, the number 3, when x becomes very, very large. Now this just means that instead of a slanted asymptote, we have a horizontal asymptote in this case. And this just shows that even if you've forgotten this rule right here to determine whether you have a slanted asymptote or not, if you simply perform the long division and then take this limit, you will also find that this function does not have a slanted asymptote, because if it were a slanted asymptote, we would get a linear function instead of this constant number. And let's now go to the fourth and final exercise. And in this exercise, we're looking at the function f of x is equal to x to the power of 3 plus 1 divided by the following polynomial, 2x squared plus 4 times x minus 1. And again, at this point you know the drill. We need to find whether this function has a slanted asymptote, and if it does, to give its equation. And as always, the first step is to find both the order of the enumerator, so x to the power of 3 plus 1, and divide this by the order of the denominator, so the order of 2x squared plus 4x minus 1. And of course, this can be very easily done. The highest power in the enumerator is 3, so we have an order of 3. And the highest power in the denominator is simply 2, so we have 3 over 2. And indeed, the enumerator is 1 plus the denominator. So indeed, we have a slanted asymptote. And again, to find the equation of our slanted asymptote, we are again going to perform long division. So we divide x to the power of 3 plus 1 by the polynomial 2x squared plus 4x minus 1. And we write our division lines just like this, and we can start the procedure. First, we divide this x to the power of 3 by this 2x squared, and the result will simply be 1 over 2x. Then we multiply what we found with each of these 3 terms in our dividing polynomial, and we write the result beneath our original polynomial. So we have 1/2 x times 2x squared, this of course becomes x to the power of 3. Then we have 1/2 x multiplied by 4x, which of course becomes plus 2x squared. And then to end off, we have 1/2 times x times minus 1, which is simply minus 1/2 x. Then we subtract both of these polynomials to get 0, minus 2x squared, plus 1/2 x, plus 1. And then the procedure just repeats itself by dividing this minus 2x squared by this 2x squared. And this of course simply gives minus 1. Then we multiply this minus 1 with each of these three terms, and we write the result beneath our original polynomial. Minus 1 multiplied by 2x squared is simply minus 2x squared. Minus 1 multiplied by 4x is simply minus 4x, and minus 1 multiplied by minus 1 is of course plus 1. Having done this, we subtract these two polynomials. We see that this minus 2x squared minus negative 2x squared becomes 0. Then we have 1/2 times x minus negative 4x, which is equal to 9 divided by 2x. And then we have this 1 minus plus 1, which is of course simply equal to 0. And again, since the term which we are left with, 9 over 2x, has a lower power of x than the first term right here, which is 2x squared, this is the end of our long division. And we conclude that our function f of x can be written as follows. The result of our long division, so 1/2 times x minus 1, plus of course our rest term divided by our original denominator, which is simply 9 over 2 times x divided by this polynomial 2x squared plus 4x minus 1. And at this point, you know the drill. What we're going to do now is take the limit of this function when x goes to plus or minus infinity. And we have to take the limit of 1/2 x minus 1 plus 9/2 x divided by this polynomial 2x squared plus 4x minus 1. And let's see what we indeed get. This term here now becomes one step more tricky because we have an x in the enumerator and we have x's in the denominator. So when x becomes very, very large, we know from our knowledge of limits of rational functions that we need to look at the highest power of x. In the enumerator, this is simply 1, x to the power of 1, and in the denominator, this is x squared. Now, if x becomes very, very large, we know that both enumerator and denominator become very, very large. However, since this is an x squared, it becomes large much faster, which means that this denominator becomes much larger than the enumerator, which means that in the limit, this term simply becomes 0. And what we are left with then is this 1/2 x minus 1, which is of course the equation for our slanted asymptote for this final function. And this brings us to the end of this video, and I hope that you're now able to look at a function and see whether it has a slanted asymptote in an eye blink, and if it does, to find the slanted asymptotes function by using long division. As always, if you have any questions, feel free to ask them in the comment section down below, or join our Discord server where we have an active community of students helping each other out. If you like this video, give it a thumbs up, and you can also consider subscribing. And with that, I thank you for watching, and I will see you in the next one. Bye.